In the last class, we studied about a TaCO2 laser, that is transversely excited atmospheric CO2 laser. We saw how population inversion is created, what is the pulsar that is used, that spark gap is used as a switch. Spark gap is nothing but two solid spheres which are connected and they are separated by a gap. So we know that spark gap is used as a switch. And we also saw the role of helium, that it has twofold role. One is, of course, depopulating 010 level, but it also stabilizes the discharge. We also saw the discharge current, that the peak current can be in kiloamperes. And we also saw the corresponding laser output. We have seen that the laser output gets delayed with respect to the current pulse. And we saw that this delay could be few hundreds of nanoseconds. And this delay is the time that is required for the gain to build up in the gain medium. And in contrast to a CWCO2 laser, we see what is called a gain switched spike or gain switched peak here. And this is absent in a CWCO2 laser. Why? Because we had very briefly seen that as gain, as excitation continues, the gain increases, and once it reaches the loss level, it slightly overshoots. And this slight overshooting is a very small in case of a CW laser, because the excitation is also rate is also very low. And here the stimulated emission sets in, so the gain is utilized, it comes down, it goes below the loss line because the gain is used up. Then again, your excitation brings it above the loss line. So this just hovers around the loss line and eventually gets clamped to the loss line. As I think I must have told you last time also, maybe you have studied this gain clamping sometime in the past. But here, in case of pulse laser, because our discharge current, as you can see, it is very sharp, the pulse duration is very small, therefore the excitation is very quick, and therefore it crosses the loss line, and before stimulated emission can set in, it further rises, and therefore this increase, this difference in the gain from the threshold, there is a lot of population inversion which is created, and this difference is leached very fast because of stimulated emission rate. Because the stimulated emission is proportional, rate is proportional to N2 minus N1, so that leaches also the population very fast, and you have this gain switch spike. We also saw that the tail is because of the presence of nitrogen atom, addition of nitrogen molecules. I'm sorry, it is written atoms here, but it is actually molecules. So the nitrogen molecules are present, and because of those, we know that there is a transfer of energy, and that continues for a longer time. And we also have seen how this temporal pulse can be tailored by changing the gas mixture. Increase nitrogen, then you have a smaller gain switched spike, but a longer tail, so that you can have probably a more, you are not worried about the damage that this might cause on some optics or something. Or on the other hand, you can actually increase this gain switch spike by increasing CO2 concentration, where you want much higher peak power. Now, having done this, we also thought that many a times you may want the laser to operate repetitively. That means you want the average power from the laser to be high. If it is giving 1 joule per pulse, and if it is giving 1 joule in 2 seconds or so, you might want to have 1 joule every millisecond, or you want to have 10 hertz, that is 10 pulses in 1 second. And so this is called repetitive operation. And repetitive operation is very important for many applications, and lasers are operated, CO2 lasers are also operated in TEA configuration in repetitive. So what is the basic difference? Well, the basic difference is that your condenser now has to be charged repeatedly. Like you see here, the condenser is charged, then it discharges, then again it is charged, again it discharges, and faster this discharging cycle, more will be the repetition rate. So every time the condenser discharges, you have a laser output. Every time the condenser discharges, there is a laser output. So if you can make the condenser get charged faster and discharge faster, then you can have repetitive. Now, for the condenser to get charged, now here, if you see here, earlier we were using a resistance in the charging loop. Now I have replaced it by a inductance. Why do we replace the charging element from a resistance to an inductance? Well, resistance is a dissipative element. You know, as the current flows through this, there is a I square R loss in the resistance. And you can probably take it as an exercise that what is the energy that is lost in resistance when the capacitor is storing an energy E or half CV square, then what will be the loss, the dissipative loss in the resistance if that is used as a charging resistance? Well, I'll give you the answer. You can actually work it out. You can deduce that whatever is the energy you are trying to store in the capacitor, that is half CV square, an equal amount of energy is actually dissipated in the charging resistance. So when you are operating it in a repetitive manner, and if you're seeing that as much energy you're storing in the capacitor is actually getting lost in the resistance also, then there are, first thing is efficiency becomes much less naturally. In addition to that, the problems of the resistance getting heated up, the problem of resistance getting shorted, etc., also increase. So we know that inductance is a non-dissipative element, and therefore many a times in place of resistance, especially when you want to go for high repetition rate operation, in place of resistance, an inductance is used. Now, what should be the values of these resistance or inductance, and how should this switch be? Okay, see, what we are saying is that the condenser should get charged, should get discharged, and again it should get charged as fast as possible and discharged. Now, as we see here, it can be a resistance or an inductance, and the condenser is getting charged, and the condenser is discharging into the laser. This is our laser, right? And this is green. Now, when the condenser discharges through the switch, okay, the switch is still in the state of conduction. See here, that means there are charge carriers here. How does the switch conduct? Here, there is a lot of plasma which is created. That means you have a lot of electrons and ions which carry the current from here to here. So when the condenser discharges, the switch is in the state of conduction. And immediately after the condenser discharges, the switch does not go into the off state. If it does not go into the off state, then this power supply can send a current through this. And what is the value of this current? This is the charging current, which is V by R. So when this flows through the conducting switch, then it can never go into the off state. If it doesn't go into the off state, then will the condenser get charged again? No, it will remain uncharged. That is because the power supply is now not able to send current for charging of the condenser. The current that is sent by the power supply is flowing through the shorted switch. So the condenser has, the switch has to recover before the condenser can get charged again. So there is a minimum current called I holdover. There is a minimum current called I holdover current. Sorry, there is a maximum current called I holdover, beyond which the if that current flows through this conducting switch, this will never recover. So the current that is flowing from the voltage source into this switch has to be less than that holdover current. If the current that is equal to V by R is greater than holdover current, then this switch will never recover. So that means what? Your R has to be large. Then only this current will be smaller. Now, if R is large, then the charging time of this capacitor, which is say 3 times RC, that is RC time constant, right? 3 times RC, that will also increase. If charging time increases, then that will also affect the repetition rate, right? So that is another disadvantage of having a resistance, because the peak current, which is V by R, flows immediately after the condenser has discharged. So now we can replace, now we are thinking that we should replace it by an inductance. Okay. Now, in case of an inductance also, this value of L has to be properly chosen to ensure that the switch doesn't remain latched. In case of an inductance, this value of this current, we know V is equal to minus L I by T. Therefore, the current I is V by L into T. So, this current now, in case of an inductance, the advantage is that at time t equal to 0, in case of resistance, what happened immediately after the condenser discharged, at time t equal to 0, the maximum current which is given by I is equal to V by R started flowing through it. And therefore, because it has to be, we have to ensure that this V by R, holdover current is more than V by R. So we had to ensure that this is maintained low. If it is maintained low, then R had to be increased. R had to be increased means our charging time was increasing. Now, in this case, at time t equal to 0, the current is 0. And as t increases, the current also increases. And this current is inversely proportional to L. So we have to choose our L so that we have to give enough time for, we have to ensure that within this time, which is called recovery time of the switch, the current does not exceed this holdover current. So that means our T has to be so chosen, our L has to be so chosen that in this time, which is called the recovery time of the switch, this V by L into T is less than I holdover. Right? So in this case, we have to, so what we say, V by L into T, where T is the recovery of the switch. For recovery, the time of recovery for a spark gap can be in milliseconds. So this T recovery, if you take as millisecond, then your L has to be such that it is less than I holdover current of the spark gap. Okay, so advantage with inductance is that your current initially, immediately after the condenser discharges, is 0. So the repetition rate that can be obtained with inductance is much higher. Further, it is also not dissipated. So an inductance is normally made use of in place of a resistance in the pulsar circuits that are used for repetitive operation of any laser for that matter, and definitely for CO2 lasers as well. And this inductance is also put in various configurations like resonant charging, command resonant charging, to make the pulsar circuits even more efficient. So the output power of the laser, average power that is obtained from the laser, can be increased by increasing the repetition rate. But here once again, you have to understand that as we are increasing the repetition rate, okay, the energy that is being dumped into the active medium is also increasing. So then the heat that is getting accumulated in the active gas mixture is also increasing, and therefore this heat has to be effectively removed. And also, because the voltages involved are very high, the currents involved are very high, the dissociation of CO2 into CO and oxygen also increases. Therefore, the usage of a catalytic reconverter is mandatory, is very, very important. Therefore, the gas mixture is basically brought out, is made to flow through a catalytic reconverter, and then it is actually cooled and then once again put into the gas mixture, into the interelectrode volume. The other thing that I was saying is that the switch, Now, this switch should also be capable of repetitive operation. A spark gap operates in arc mode. That means between the electrodes, as we saw just now, there is a lot of plasma which is created. You have electrons and ions, and the number densities are very large. And therefore, recovery, when we say, as we saw, that for repetitive operation, the switch has to recover. And the recovery of spark gap is difficult because these species have to move out of this zone. Only when they move out of zone, that this will again become capable of holding that same voltage, right? Because it has to also hold that voltage that we are giving. So this should be capable of holding that voltage. For that, the species, ions and electrons which are created in between, they have to be removed. And that is difficult for a spark gap because that number density is very large. So normally for repetitive operation, thyratron, which works in vacuum, that is made use of. And also modified spark gaps also are tried. But thyratron is the go-to switch when one operates lasers, CO2 lasers in repetitive mode. So now we now know that the CO2 laser is can be operated in pulsed mode, CW mode, low pressure, high pressure. We also saw that it operates, it is capable of being tuned, although discretely, generally, in the 9 to 11 micron region. This we have repeated many number of times. And that there are two bands which are possible. One is 10 micron and the other is 9 micron band. And in each of these bands, the 10 micron and the 9 micron, you have P branch and R branch depending on this delta J rule, that for emission, when delta J is +1, you have P branch, and when delta J is equal to -1, you have R branch, right? So in each 10 micron band and 9 micron band, you have P and R branches. The 10 micron band has much higher gain as compared to 9 micron band, some 10 to 12 times more than 9 micron band. And within the two branches, that is P branch and R branch also, P branch is of larger wavelength as compared to the R branch. And we know that gain is proportional to lambda square, right? So the gain for P branch is more. Okay, so these are the basic facts. Now, when we operate a CO2 laser under free running condition, we have said that it normally operates on 10p20 or 10p18 because gain is more thick. Okay, now let us try to understand this a little more in depth, that what can be the emission feature of a CO2 laser and how is it possible that we may discretely tune it. Say we want to operate on 9 micron band or we want to operate on a particular 10p branch line, then what is the way by which we can go about? But before going into that, it would be worthwhile for us to spend a little time on, yeah, so here I have shown you that you have, this is the 10 micron branch, this is the 9 micron branch, you have the P branch lines, you have the R branch lines, and the separation between P branch lines is a little more as compared to R branch lines, and that you will easily understand if you try to find out what is the energy difference, how a P branch line is originating, how an R branch line is originating, and what is the kind of energy difference that entails, and then you will be able to understand that why this is a little more and why this is a little less. Now, before understanding how we can actually get the kind of spectrum that we want from a laser, from a CO2 laser, or what it will naturally give rise to, what kind of output it will naturally give rise to in terms of spectroscopic content when it is in a free running mode, let us try to just understand a little about how an atom or a molecule which is in the excited state, when it comes down, what kind of a spectrum it gives. Consider now molecule which has two states, E1 and E2, separated by an energy gap, such that if the molecule comes from the upper level to the lower level, then it can give rise to a photon whose frequency is given by the difference divided by h, right? So now if I try to see the spectrum, what is meant by spectrum? It is basically the intensity or the number of photons which are coming as a function of frequency. So when we see that, we expect, isn't it? What would you expect? We are saying that this is E1 and E2, E1 and E0, the difference is delta E, and nu zero is delta E by H. So then you would expect that you would get a single frequency emission. So it should be just line at nu zero. But is it possible? Do you really get a single frequency emission when you have created inversion between E1 and E0? No. That is because, why it is so? It is because this excited state does not have infinite lifetime. This situation, this excited state does not have infinite time. In fact, it has only finite lifetime. When you say finite lifetime, that means delta T, there is an uncertainty in whether the molecule will be there. When you say lifetime, lifetime means that in this, if a particular level has a lifetime T, then in time T, about 66% of the population comes down. That means only 33% remains in that particular level. Right? So when we say, when we are talking about an excited level, it does not have infinite lifetime, but it has a very finite lifetime. And that, because it has a finite lifetime, because there is an uncertainty in the lifetime, there is a corresponding uncertainty in energy also. And this comes from Heisenberg's uncertainty relation. Delta E, delta T is always greater than or equal to h by 2 pi. So we know that there is an uncertainty in delta T. So there has to be a corresponding uncertainty in energy also, which means that our excited level is not a discrete level like this, but actually it is spread. As you can see, it is spread about the mean energy, about its central energy. And when there is a transition from here to here, if you see number of molecules which you have taken into E1 and you see how each one is coming down, then you will see that it is not at nu zero that you will get the output, but it will be spread about nu zero. As you can see here, it is spread about nu zero with peak being at nu zero and it gradually falling off on either sides. So that means that because you have the energy level, upper excited level, not being discrete, but having a finite width. So when a molecule or an atom, actually, when it makes a transition from the excited to the lower level, it does not, when you consider a number of atoms, of course, no? So that is where you see that it gives rise to such a kind of distribution. And this width is called the natural line width or natural broadening of the energy level. And this is an intrinsic, it depends on the intrinsic spectroscopic properties of the levels that are involved in transition. This lifetime is also called radiative lifetime, natural lifetime, or the spontaneous lifetime of a particular energy level. Now, at this point, maybe so you can see that short-lived, if you have a short-lived excited level, upper level, that means delta T is very small. So then how would the energy spread be? Delta E then will be very large. I would like to know from you what would be the broadening of the ground state. You can just think and try to see if you can answer this question. What would be the lifetime of the ground level. Okay. Now, this is about spontaneous lifetime, and any excited species, any excited energy level will have a certain broadening, which depends on its spectroscopic properties. Now, suppose we take large number of molecules, an ensemble of large number of molecules, and in that we pick one molecule or one atom. See, this, whatever we are talking, this is applicable to atoms also, it is applicable to molecules also. So I may use molecules or atoms synonymously. So you please do understand that it is a very broad concept which is applicable in general. So now suppose in that, from that broad ensemble, suppose I take a molecule, I excite it, and I try to see what is the frequency of de-excitation. I excite it once again, see the de-excitation. So I try to see it for a long period, okay? And I try to monitor what is the frequency of emission. And you will see that what you see is not at one frequency. Now you know that it will not definitely be at one central frequency, but it is spread about the central frequency. As you can see here, it is spread about the central frequency, and this spread is more than what we had thought. Just the natural broadening that we know of that particular level, it will be more than that. Okay. Now this is for one atom. I take another atom, I mark it, and then I repeat the same experiment. I excite it, and then I try to see the de-excitation. What is the frequency? And I repeat this experiment n number of times, n tending to very large number. And I see again that the molecule will emit with a given frequency within this fluorescence profile. This is the proof. And I see that it is very similar, identical to the previous one. I repeat this with many atoms or many molecules, and I find that they are all identical. And therefore, I can say that this is the fluorescence profile of all atoms put together. Can you see this? So this is the fluorescence profile of all atoms put together, and it is identical to that of any atom. That means what? That means that all these atoms are identical in respect of their emission. So this, so then why then is it not same as that your fluorescence, that spontaneous emission width? Why we are saying that this is a little more? Well, you see, we have taken an ensemble of molecules. These molecules are in constant collisions with each other, and collision with a molecule which is in its upper level, it reduces its lifetime. It forces it to come down, and therefore there is a change in its lifetime. So it reduces its lifetime, and therefore it results in a broadening. And this broadening we have seen is identical for all the atoms which are constituting that ensemble, all molecules which may be constituting that ensemble. So such kind of broadening we say is homogeneous broadening. Collision broadening is one such homogeneous broadening. Okay then, so what we have learned today is that we have seen pulsed operation of a TeCO2 laser. We have also seen repetitive operation of a CO2 laser. We have seen why the excited species, when it comes down, there is a broadening of the energy level, that is called spontaneous broadening. And also we have touched upon today, we have seen to some extent what is homogeneous broadening. That is where all molecules of which constitute the ensemble, they are identical, they have the same fluorescence profile. So they have the probability of emission within that fluorescence profile with equal probability.